Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we are going to be talking about the centroid of a triangle. To get started, let's review some of these centers we have actually seen in previous Thursday Tidbit videos. So in a triangle, we've talked about the center of the incircle. So if you have a triangle, you draw a circle inside of that triangle. That centers the incenter, and it is the intersection of the three angle bisectors of the triangle. So you can get that center without even talking about that circle if you like. You take the three angle bisectors, or really you just need two of them, where they intersect, that is the incenter. The circumcenter is the intersection of the three perpendicular bisectors. This is the center of the circle drawn around the outside of that triangle. So these are two of what we would call centers in a triangle. These are centers in a very natural sense in that they are the center of an incircle. Now today's video we're going to be talking about a centroid, which is actually referred to as another center of a triangle, and we'll say why in a little bit as well. But first, let's just review the median. So in a triangle, a median, this is going to be one of our important concepts of the day. It connects one vertex of the triangle to the midpoint of the other side. So of course, if we have a midpoint, this is telling us that BD is equal to CD. And then this could be drawn from any vertex, of course. So any triangle, again, has three medians. Here we're just looking at one of them. Now, one of the important facts that we're going to use a bunch today is that these two triangles that the median divides the big triangle into, these two triangles ABD and ACD have the same area. So this is something we've seen before in terms of some of these ratios and things like that. They both share the same height, so their areas are proportional to their bases, but since we have a midpoint, we have the same area in both cases. So this one's a pretty straightforward fact, but it's going to come up a lot when we do the properties of a centroid on the next couple of slides. Now, why is this called, or what is the centroid there, and why is it called a center? Well, it's a center in the same sense that it's the intersection of these different lines in the triangle. So if we look at the three medians of a triangle, we have AD, BE, and CF, and they all intersect at the same point, and this point is what's called the centroid. So this is a fact you might need to prove. You can prove it using some of the methods we'll talk about a little bit later in this video as well, but we have our centroid here, the intersection of the three medians, right? It's not obvious that all three of those line segments intersect at the exact same point, but they do, and that point is the centroid of a triangle. Now we're going to do a couple of properties there. The two most important ones are going to be the second and third ones we do. Those are the more proof ones we'll look at quick. But the first one is why the centroid is also called a center. If you have a perfectly uniform piece of cardboard or paper or wood or something like that, the centroid is the center of mass. So that is where a real center comes out of this centroid. Remember, the center of mass then would be, so if we cut out this triangle on a piece of paper and we wanted to balance it, that centroid would be the exact point we would want to balance that triangle on. So this could change based on the shape of the triangle, things like that as well. So that's one of the key pieces of information, one of the real world applications of the centroid. Now let's start to get into some geometric properties here as well. And these we can look at a little bit of proofs of quick, because they're actually pretty instructive to do and helpful as well. Now the first fact, this is one of the very important facts for a centroid. Well, it's really talking about the medians. But the three medians all intersecting at this centroid of a triangle divided into 6 triangles of equal area. So we mean these 6 little triangles that we have along the outside, they all have the same area. Now, I'm not going to draw them all of the same color right now, and that's a good place to start for this if we're going to start thinking about how we might prove this fact. So these are the 6 triangles, however. Notice I'm coloring them the same when they're on the same side of the big triangle. Now, why is that important, and why is that our starting place for this problem and the proof we have here? Well, pretty clearly, because of this median and midpoint stuff, all of these have the same area as pairs. So what do I mean by that? I mean that this blue triangle and this blue triangle both have area X, let's say. These two triangles clearly have area Y, and these two on the bottom clearly have area Z. So we can look at those as pairs of triangles, right, that have shared height in the same base, so they have the same area. But remember our fact from before. Remember we said any median divides the big triangle into 2 triangles of equal area. So what if we look at, for example, triangle ABD? These aren't congruent or anything, but if we look at triangle ABD and ACD, those 2 triangles have the same area. Their areas are the same. Well, wait a second. We can write their areas in terms of the smaller areas we have here. So this tells us that 2x plus z, that is the area of ABD, that area has to be equal to 2y plus z. Well, even if you don't know much algebra, it's easy to see those z's cancel out, the 2's can cancel out. We must have that x is equal to y as well. So then we have 2 pairs on the side, x equals y in this case. Now, I'm not going to write out all of the details there, but similarly, right, we can draw the same type of conclusion to say that, for example, 2x plus y is equal to 2z plus y. And so we have the same thing there that tells us x equals z. So our big conclusion that we can make, therefore, we know that x equals y equals z, and we've divided this big triangle up into 6 equal pieces here as well. So that's what we can say in terms of these medians and centroid dividing our shape up into triangles of equal area. I just want to stress one more time, we're just saying they have equal areas. Even the 2 blue triangles, the 2 green triangles, the 2 red triangles, they're not necessarily congruent or similar or any of that. They are different triangles possibly, but they for sure have the same area. Now, that is the one famous fact you should definitely remember. And in fact, that's the most important one because we can use that fact to do the other most famous fact here. And the second most famous fact is that the centroid divides each median of a triangle in a 2-to-1 ratio. So for example, what is this saying here? This is saying that if we look at the ratio AG, so if we call G the centroid, the ratio AG to GD, that ratio is 2-to-1 in this case. So that AG is 2 parts, and then the GD is 1 part. And of course, this doesn't matter which ratios we look at. This is the same for BG to GE. Of course, AG and BG don't have to have the same length or anything. We're just saying that all of these ratios, every time you draw the centroid on a median, it cuts that median into 2 pieces. One piece is twice the length of the other piece there. Now, let's just look at one of these that's the easiest to visualize. Here, the proofs of all of these are exactly the same. But let's look at BG to GE in this case, and we want to show that this ratio is equal to 2 to 1 here. And again, we can look at these in terms of triangles. So let's look at this triangle BGA. And let's say that that again, staying with the variables from the previous slide, has an area of 2x. So the area of ABG is 2x in this case. But what about the area of AGE? Well, now that we know all of these pieces are the same, that has an area of x in that case there. So the area of ABG is equal to 2x. So if we look at this ratio of areas, what do we have here? We have this 2 to 1 ratio in terms of areas. So ratio of areas. And remember, this is a little bit of an extension of this midpoint equal areas stuff. But remember then, if we have this 2 to 1 ratio, 2x to x in terms of the ratio of areas, because they both share the same height. If you look at it this way, that's why I picked this triangle, of course. We draw this height down from here. They have the same height in this case. That means that that ratio of areas is actually just the ratio of bases. So if we look at that ratio of areas, it's BG to GE. And lo and behold, that's exactly what we want. That is the 2 to 1 ratio we're trying to prove in this case. So that's why I stress the 6 equal areas, because then very, very quickly, if you're thinking of just those areas, you can derive and understand where this 2 to 1 ratio comes from for the centroid. Now let's look at one more example here. And let's use this as an excuse to put some of our knowledge that we just did into action here. So we have a triangle ABC, and we know that AB is equal to 8, and we know the 2 other medians are equal length. So let's draw a version of this triangle here. So we have AB at the bottom in this case. And I want to think of AB on the bottom because then we have our 2 equal median lengths coming up from there. So we have our 2 medians there of length 7.5. My picture here might not be perfectly to scale or anything. And then if we wanted to, we can of course extend this into a triangle as well. So I might modify these medians a tiny bit here with that triangle drawn as well. But I just wanted to stress that you could think of this as the medians are drawn first, and then we can go from there. Then you could extend those sides to make the triangles here. Okay, so let's label some of these points in this scenario. So we have AD, we have BE in this case, and I guess let me move everything down real quick so we get C at the top. And one thing that probably shouldn't surprise you, we already have our centroid on this picture, but let me just draw the last median in here as well. Let me connect C and draw this to point F, And let's look at some of this information we have now about these triangles, and our centroid is of course going to be relevant for this problem. Now, let's look at a couple of things here. So, let's think about our 2-to-1 ratio that we were just talking about on the previous slide, right? We know that AD and BE is 7.5 in this scenario. But what else do we know? We also know the centroid divides each of those medians into equal lengths there, right? So we know that AG, the ratio of AG to GD, that is equal to 2-to-1, which is also the ratio of BG to GE. So this is BG to GE as well. But wait a second. That tells us the lengths. We know they're in a 2-to-1 ratio. They add up to 7.5. So GD and GE are 1/3 of that, 2.5. And the more important one for our problem, it turns out, is that AG and BG are going to be 2/3 of that. So AG is actually the same length as BG here, which is 2/3 of 7.5. Which is 5 in this case. So just so we have that written out in detail here, we know that that length is going to be 5 here as well. Now, wait a second. We have CF is a centroid, or is the median as well. So that gives us that we have AF is 4, right? 8 divided into 2 pieces is 4, and 4 in this case. Now I'm going to say this verbally, but in fact, AFG and BFG, from this point, it's not too hard to see they have 3 equal sides. We have 5, 4, and then some mystery side there. So those 2 triangles are congruent. But how can you have 2 congruent triangles that are a straight line in there? They have to be right triangles. So in fact, we have both AGF and BFG are congruent right triangles. So in fact, we can find the mystery length GF there as well. So let me just write it out like this. AFG is congruent to BFG. And both are, in this case, 3, 4, 5 right triangles there. So these are 3, 4, 5 triangles in this case. Both of them are 3, 4, 5 triangles here. In fact, we've pretty much shown now what you would need to convince yourself that we actually have an isosceles triangle. So as a little bit of extra here, if you want to convince yourself that we actually have an isosceles triangle in this case, anytime actually that you have 2 equal medians, you have an isosceles triangle there. Now, there's a couple of ways to finish this problem. From here, we could find the length of CF, that's the height of the triangle, and then use a half times base times height. But just to find or practice our other fact here as well, since we already know AFG is a 3, 4, 5 right triangle, the total area, so if we look at the total area here, is going to be 6 times that triangle, right? So our total area is 6 times the area of AFG, so it's 6 times 1/2 times 3 times 4. So that is an area of 6 times 6 is equal to 36 here. So you could use this property then where once you find one area for the 6 triangles, even if they're not all congruent, but they all have an area of 6, and that gives us our answer from there. So this is a good way to practice these last 2 facts we had for centroids. Now, there's more centers out there. There's a lot more stuff you can do with centroids and incenters and circumcenters, all of those things. But just getting comfortable with centroids is a good place to start. And there's some cool problems you can solve using just these two facts that we talked about on the previous slides. But that will do it for today's Thursday Tidbit. Check back every Thursday for a new math tidbit in 2021. Stay tuned for some plans we might have for 2022. And if you like this, please like our pages, subscribe, and I really recommend checking out ziml.areteem.org if you want some more practice and other resources as well. Goodbye, everyone.